right. So thank you very much, Silvia, for the introduction. I hope you can see my screen. And thank you to the whole group of financial computing for having me for this seminar. It's a pleasure to be presenting this very recent work that we did together with our group leader, Claudio Tessone, at the University of Zurich, and with a collaboration with Dr. Marco Del Rico from the European Central Bank. And the topic is that of the velocity of money, which is a very established concept for economics, macroeconomics, for over 100 years at this point. And we take a microeconomic spin to it, and I will try to be as clear as possible on what I mean by this. So the title is MicroVelocity, as Silvia already said, and let's start by framing the problem that we treat. So first of all, we are kind of fascinated by this rise of digital currency in its many forms that are constantly growing in number and in usage right now. So digital currencies have been there. Digital money has been there for a while now, but over the recent years, and the pandemic has helped as well, and the cryptocurrencies and so on have also helped. It has become more and more popular, and so this is something that motivates us in a way, in the sense that we say digital currencies are not only a very nice thing for the public, but maybe they will also be useful for policymakers or for regulators as novel policy channels. So in order to be able to do something like that, we need to be able to leverage on this new source of data to measure relevant quantities that must inform policy making and so on. So in this particular work, we look at the velocity of money, which is, as I said, an established concept from macroeconomics, and we give it a microeconomic spin. What I mean by microeconomic is that, of course, we look at how transactions happen in a real economic system, and then we go from there to build up to the concept of velocity of money. And cryptocurrencies in this thing are an ideal sandbox, because of course digital money takes many forms, and it has become more and more popular, but getting data is not straightforward. Cryptocurrencies are amazing in the sense that they allow you to have a lot of data for free, basically, and to test measures and concepts over there that then might be transferred to other kinds of systems. So a couple of research questions that we try to answer with our work. First of all, do different economic agents, as I said, I'm looking at the micro perspective. So agents are individuals that participate in an economy. And the question is whether they contribute differently to the movement of money, and so in particular to its velocity. And not only this, but of course, if they contribute differently, how these differences are related to differences in other factors. So maybe it's wealth or centrality in the economy, and so on and so forth. Maybe many other covariates that may be helping in characterizing how agents behave. So let's start by the very basics, from the very basics. And what is the velocity of money? So velocity of money has been there, as I said, for over 100 years. And its easiest way of presenting it comes from the Fisher's equation of exchange, where you have this identity between the product of the monetary mass and the velocity. On the other end, and on the other side, you have the average price of goods and services in the economy times the number of units of goods and services in the economy. So the velocity, which is introduced precisely to make this an accounting identity, so that this works, represents the average number of times that a given unit of currency changes hands over a given time period. So the time period where I measure the nominal economic output is also the same time period where I measure the velocity, and where I assume that I can measure velocity, and so the average number of times a unit of currency changes hands in that time period, right? So this is very in abstract, very macro, of course. And why do you want to know what is the velocity of money? Why is it useful? The velocity of money is useful in this sense because it helps in understanding what is the demand for money in an economy. And in particular, if you have a velocity which is too high, it might be a problem because there is low money demand, because basically it means that as soon as I get money, I spend it immediately because I see more rewarding assets to hold. Or maybe I'm scared because there is negative yield to the money, to holding money, because there is a high inflation. And this may also introduce a feedback loop, because of course, if I spend immediately, I may also contribute to inflation in this case. On the other hand, if you find a very low velocity, it might be a sign that the economy is stagnating, because I get money and I never spend it. And I just, basically circulation of money goes down. But the question then is, what is the velocity at the level of transactions, no? At the level of individuals? So, as I said, velocity is the average number average number of times that a unit of currency is used in a transaction, but it's hard to imagine to be able to observe this, right? To be able to measure how many times a given unit of money, the same coin, is exchanged, right? However, one can start by doing some very simple arguments, and in this nice paper from 2003, the authors give a microeconomic argument, microeconomic foundation to construct the macroeconomic velocity. So I will briefly review this argument, and then I will show what is the addition that we made to this argument that is relevant to the case at hand. And so let's start by introducing what is the most important quantity in this framework, which is a random variable tau, which is representing the holding time of a coin. So the time that a given coin stays idle in the pockets of someone between two transactions. Okay, so this is a random variable, and as a random variable, we'll have some probability distribution. And given these premises, it's easy to see that multiplying the probability distribution at tau times the differential times the total number of coins, the monetary mass in the economy, you get the fraction of coins in the economy that have a holding time tau, right? Okay, so this is very straightforward. Then what is the flow that this fraction of money generates in the economy? So let's assume that we are a stationarity, so that everything is simple because the probability doesn't change, everything is there. And it's easy to see then, since every unit of money in this fraction of supply has a holding time of tau, it will be contributing 1 over tau to the flow at any time, because it does a transaction every tau units of time. And so the money flow generated by this fraction of money is this f of tau, and the total flow is just the integral over tau over this of this flow. But then, by definition, the total flow is equal to the product of the prices times the nominal economic output, because that's the definition of the price level and the nominal economic output. So PQ is the total flow of money in the economy, and it is also equal to M times V. And so this gives us the definition of velocity starting from microeconomic principles. So this is where the paper of Wang and others in 2003 stops, but this is also where we start with our argument. So, of course, once you have this framework set up, it looks very nice, but it's also, you haven't really solved the problem, right? Because you still need to measure this probability distribution of holding times, and so you're back to square one. Well, here is where we get some advantage from having access to very large data sets of transactions, in particular to blockchains, right? So in a blockchain, you have access to the full, in a public blockchain, you have access to the full transaction history, but not only. In blockchains that are based on the UTXO protocol, the unspent transaction output protocol, like Bitcoin and many others, you actually have the information about the holding time. What do I mean? What do I mean by this? In a UTXO blockchain, you have, every time you spend some money, to reference the time at which you got that money. This is exemplified by the figure here. So you see that at block T, Bob receives some Bitcoins from Alice and Dan, and then he goes to spend the 1 Bitcoin that he got from Alice and give it to Edgar at time block T plus tau. So this Bitcoin will have a holding time of tau blocks. And the same goes for the half Bitcoin that Bob gives to Franz because he received it tau plus sigma blocks ago. So we are able, thanks to the way in which the accounting goes in this kind of blockchains, to actually measure these holding times and to characterize. This is not the only thing that we do. We also do a couple of additional considerations. So first of all, this is very trivial. Since events happen only within blocks, it doesn't really make sense to stay in continuous time. So we switch our treatment of the problem to a discrete time where time is indexed by the number of blocks that have passed in the blockchain. And we also do another refinement, which is that there is no real reason to believe that different coins have a different holding time because of their intrinsic properties. The main reason why you would expect them to have different holding times is because they belong to different people. So we factorize, we condition this probability distribution of holding times depending on ownership, right? So what we end up with after this couple of transformation is this formula. So the formula that you see here is now a sum, it's not anymore an integral because we are in discrete time. It starts at 1 because it doesn't really make sense to have a holding time of 0, because having a holding time of 0 means that I get and spend everything immediately, so I never actually hold the money. And now you see that here there is a pi of tau, and pi of tau is the fraction of coins that is being held for tau blocks by agent I. So this formula gives us what we call the microvelocity, which is the individual contribution of a given agent to the total velocity of money. And the nice property is the third one that I show here, is that the sum over all agents in the economy of these contributions sums up to the total velocity of money in the economy. So this is a very interesting, I would say, and very nice property, because it allows us now not only to measure velocity, which is fine, but we could have done it in many other ways, but also to analyze its distributional aspects, because now we can look at how different agents contribute to it and try to figure out why and how they do. So let's go back to our example just to clarify things a bit. We are now interested in measuring the velocity contribution that Bob is producing. And so we see that between block T and T plus tau, Bob is holding 1.5 Bitcoin. 1 Bitcoin is a holding time of tau. And so it will contribute 1 over tau, and alpha Bitcoin will contribute tau plus sigma because it's spent after tau plus sigma blocks. So between these two blocks, the velocity that Bob contributes is 1 over tau plus alpha over tau plus sigma. And then between block T plus tau and T plus tau plus sigma, it's going to be 0.5 over tau plus sigma. All right. So I've been speaking about agents. Now, of course, blockchains are pseudonymous, at least, or like they try to preserve anonymity, right? So basically what you have on blockchains, I'm pretty sure most of the people here knows but I'm going to repeat it probably. On blockchains, you have pseudonymous identities, which are named addresses, and they are strings of numbers and letters that are referring to specific amount of coins that are available to that address. But of course, a single agent may own any number of addresses, basically. You know? So it may have access to any number of addresses, and there is no limitation really there. So the problem then is if we are to measure velocity of money, we want to measure transactions. We don't want to measure accounting transactions. We don't want to measure when I move my funds from my right pocket to my left pocket, because that's not really an economic transaction. So what you need to do is try to de-anonymize, in this case, the blockchain data, in order to spot what are the transactions that are to be discarded. There are several ways of doing this. In particular, we use three, which are based on heuristical arguments and that are basically exploiting some mechanisms that arise in the wallet management softwares. And the easier one to use is that in this kind of framework, in this kind of blockchains, when you have a transaction, you may have multiple inputs. But in order to be able to write the transaction, to send the transaction, you need to sign all the inputs of the transactions. And so basically, either you have access to all the signatures because the other people that belong to in the transaction with you have given you access to those signatures, or you are the one that holds the signatures in any way. So basically, if multiple addresses appear as input of the same transactions, we more or less consider them to belong to the same agent. I say more or less because there are some cases that are clear when you can discard this kind of heuristic, but I'm not going into the detail about that. The second kind of heuristic argument that you can use is that given the protocol, again, the UTXO protocol, basically everything that goes into a transaction needs to go out of the transaction. So the sum of inputs needs to be coinciding with the sum of outputs. But the problem is that most of the times, maybe you don't really want to send the whole amount that you are inputting to the destination of the transaction. So what you need to do is to create a new address that you call a change address, which belongs to you, and where you send any spare change from the transaction. So in this case, for instance, if you look at T0, the transaction, the first transaction that I'm showing, the intent of the sender was to send 5 Bitcoins to this guy, the yellow guy, but he doesn't have access to any address that has 5 Bitcoins over there, so he has to send 5.88, and the change, the 0.88, is redirected to another address. How do you spot this? Well, you can say that if you find an address in the output whose value is smaller than the value of any of the inputs, this is likely to be generated as a change address, because basically there was no way of including less inputs, and I just had some spare change. The third and final kind of pattern that you can try to spot is what is called a peeling chain. So some addresses hold a very large amount of coins, a very large amount of tokens, and they will never spend them in one go. So what they will do is they will slowly erode them by multiple transactions that have the same pattern, which is the same as having only one address as an input and 2 addresses as outputs, and then one of the outputs is recycled as another part of the same pattern. So it's still 1 input and 2 outputs, and so on and so forth. So basically, the addresses that link up this chain are considered to be belonging to the same agent, because you say, okay, this is just one address that is being slowly eroded by the owner. Okay, but this may be very technical and just not very interesting, maybe. So we'll just finish this section by saying that we do some robustness checks on this aggregation. So basically, we select either a very safe heuristic algorithm, which is just using only the multiple inputs, or a more forgiving, more aggregating algorithm, which is a combination of the three that I presented. But the results are largely unchanged by this, so they're more or less robust to this. So let's look at the data that we are using. So as in all my examples, I've talked about Bitcoin. I've been talking about Bitcoin and the fact that this is the protocol that we have in mind. Unfortunately, Bitcoin is still a bit too large for our capabilities in the sense that it has too many transactions to analyze, and we haven't really been able to optimize our code to do this. So we actually implemented our analysis only on 4 altcoins that are smaller than Bitcoin, but they use a very similar protocol. So 2 are very small. One is Monocoin and Feathercoin. We use them mostly for proof of concepts. But the ones that are a bit more popular and a bit more beefy in terms of how much money circulates over there are Dogecoin and Litecoin, which are among the most popular right now, but not as popular as Bitcoin, of course. So we do this analysis of measuring this MicroVelocity on these 4 coins, and now I can go to a bit of results. So first point that we want to check is, of course, my claim that the total sum of these MicroVelocities goes and approximates very well, or at least, I mean, it should be exactly the total velocity of money, right? Well, of course, we have a way of estimating the total velocity of money, which is measuring the flow over a given amount of time and dividing by the money supply. So this is what we did, and that is the x-axis over there, and on the y-axis instead you have the total velocity of money. So you see that the 2 measures are mostly in agreement. There is some variability around the diagonal line. The reason for this variability is mostly that PQ over M here is measured on weekly segments, and a week is a relatively short period of time, so you will have a very noisy estimation of velocity on that from that quantity. But we wanted to have enough points to show some relation here, so we went with the weekly time scale. And also, if you measure PQ over M weekly, basically you neglect any longer periodicity in your transactions, basically. You know? So basically you can never spot transactions that happen every month or something like this. Whereas in our treatment of MicroVelocity, also transactions that happen on longer frequencies or longer time scales are counted at any point in time. But still, the agreement is pretty much there. So we are very happy with this. Then, of course, I talked about distribution of MicroVelocity. So how is this VI distributed across agents? So we did a couple of tests, statistical tests, to see what is the behavior that we find. And first of all, we tried with a Gaussian, because of course, why not? And a Shapiro-Wilk test basically strongly rejects Gaussianity. This is not even a symmetric distribution, actually. So it doesn't really make sense to talk about Gaussian here. Then we tried with thin-tail distributions like an exponential. And again, we have a very poor fit. You see here the pastel colors in these plots are the Kolmogorov mean of distance between the best fit of an exponential distribution and the distribution that we find for velocities for MicroVelocities in the data. So basically as far as possible from there. Whereas if you take a fat tail distribution, like a power law distribution or a normal distribution, this is a lot closer to what we measure. So the key conclusion that you can get from this is that at least the distribution is very heterogeneous, and most of the total velocity is actually determined by relatively few agents. So this is a very qualitative argument, but let's try to look at some snapshots that we have. Here on the left, you have a day in 2016. It's 8th of April in 2016. And on the right, you have the 4th of April in 2019. And this is the distribution of microvelocities normalized by the total velocity, the cumulative distribution of microvelocities in these 4 cryptocurrencies that we analyze. And you see as a reference, I plotted a Pareto distribution with the exponent of 1.65. I'm not arguing that this is a Pareto distribution at all, but I'm just saying that it looks very close to a power law distribution, at least. And to be a bit more quantitative rather than qualitative, we also try to do some distribution fitting. And so we fitted the power law distribution to this data, and we see that it has an exponent which is here you see some statistics over weekly sampled distributions, and you see that the exponent that you estimate is typically between 1.5 and 1.7 for all these coins. What we also did is looking at the statistics for the Kolmogorov-Smirnov distance, and in particular, we looked at how many of these of the Kolmogorov-Smirnov tests would be rejected against a Pareto distribution null hypothesis at a 20% confidence level, so very, very broad. And most of the, if not all, of the tests of the Kolmogorov-Smirnov test do not reject the Pareto null hypothesis, the power law null hypothesis at the 20% level. So I mean, very a relatively strong non-rejection. And the opposite is true instead for an exponential distribution, where of course, as I was showing before, the Kolmogorov-Smirnov distance is so large, and basically, even with a very forgiving confidence interval, you will never get a non-rejection. So, in summary, how is the microvelocity distributed? It's very fat-tailed. And by very fat-tailed, I mean this. So, you see here in these figures, the stacked areas, you see the contribution by the top 5 agents, the 5 agents that we identify having most of the more velocity, in a given snapshot. Again, these weekly snapshots, and in blue is all the others, right? So number 1 to 5 are the top ones, and then the blue is the rest of the agents. And you see that basically most of the velocity is dictated by just very, very few agents, like 1, 2, maybe 5 agents, depending on time. And this is mostly true for the smaller ones, in particular Monacoin and Feathercoin. You see that the others, besides the top 5, are basically non-existent, or just, I mean, less than 20% or less than 10%. And again, there are tens of thousands of agents active at any point in time. So here is just a very tiny fraction of the ones that are active. So you might argue, of course, that this is a problem with over-aggregation. We might have one very large agent that is just because it's too aggregated by the heuristic algorithm that you use. What happens if I use a much more conservative heuristic? Not much. Like, it's very similar still. The others are still contributing less than 50%. Litecoin is a bit more. It's a bit less heterogeneous, but for the others, it's still very, very heterogeneous. And on the top side here, I reported the number of times that the same agent figures in this top 5, and you see that in particular for Monacoin and Feathercoin, the top 2 are relatively persistent in this top 5 as a fraction of the weeks that you find in the sample. So to ask more questions, how are these agents characterized in terms of their velocity and other characteristics that they hold? So in particular, what is the relation between velocity and wealth? And we find that this is very strongly correlated. Here, the big plot is a Spearman rank correlation between microvelocity and wealth. So it's very strong rank correlation coefficient, and I reported 4 snapshots at some random dates in between, just to show how it goes. So it's very close to a diagonal line with some variability around. This is not really surprising, maybe, because of course, in the formula that we had for microvelocity, we saw that this is a weighted average in terms of the wealth, because MI is the fraction of money supply that is, is the money supply that I holds at time t, and this will basically imply that there is this linear relation. But still, there is some variability around this this line. So this is not only explained by wealth, basically. Finally, let's go and look at some more structural properties of agents. And in particular, we look at transaction networks. So we build transaction networks by identifying agents as nodes in the network, and transactions are directed links from one agent to the other. So when the green agent sends a transaction to the blue agent, there will be a link going from green to blue, and the same for all others. And of course, there is the question of what is the time aggregation that you use, because you may take the cumulative transaction network, where you consider that if there has ever been a transaction between these two, they are connected. We argue that this is not really significant in this case, because of course, it doesn't really matter if 10 years ago we had a transaction now. So I want to know if I'm central now, not if I've been central over the whole history. And so you could also go to the to the block time if you want. This again, this is not really interesting, because then you have very few nodes and transactions. So we select a nice sweet spot in between, which is the weekly time scale, where you basically can get rid of inter-week effects, intra-week effects, where basically you have like weekend effects of these sort of things, that those are ruled out, but you still have a nice causality between transactions over longer time scales. All right, so we have transaction networks which are weekly. So they, again, on a given week, I will have nodes that have been active in that week, and links that connect them if they have at least one transaction between them in that week. And on top of these networks, we put our measure of microvelocity. So I take the microvelocities and I put it as an attribute to the node in the network. And then I go and look at, in this case, at the assortativity coefficient for this metric. So basically, I look at what is the correlation, in this case, the rank correlation, actually, between microvelocities if the two agents are connected in the transaction network. And we see that it is typically negative. So basically, neighboring nodes will have very different velocities. Typically, one has high velocity and the other one will have low velocity. So this we find that this is interesting, because this is pointing out to some is further evidence basically towards the argument that intermediation is a big thing, especially on blockchains. And on blockchains, you will find that basically there has been a recent paper that was pointing out that on Bitcoin, the vast majority of transaction is basically accounting between exchanges. So it's a rebalancing of portfolios and so on between exchanges. It's not between end users of the tokens. So this is more or less pointing to that. Basically, you have high velocity intermediaries and low velocity nodes that gather around those intermediaries. And this is further confirmed, I would say, or reinforced by measuring what is the fraction of microvelocity, what is the fraction of total velocity that is in the core of the network. So we did a core periphery subdivision of the network using the very simple and very fast algorithm of LEAP. And basically here I'm plotting the ratio between the fraction of velocity that is in the core and the fraction of nodes that is in the core. So if this is larger than 1, it means that there is more velocity in the core than it would be justified by a uniform distribution between core and periphery of the network. And this is always larger than 1 and can get very much larger than 1. So basically, there is a lot of the velocity is produced in the core of the network, and the periphery of the network basically is contributing very little to it. Okay, so with this, I will go and conclude so that we can open the floor for comments and questions. And I have a couple of take-home messages from what I presented. Basically, we introduced this MicroVelocity as a bridge between the micro representation of transactions and so on, and the macro representation of this velocity of money. One point that appears more or less clearly from my results is that despite the statutory decentralization that cryptocurrencies have always publicized and marketed, the flow is very centralized, and MicroVelocity shows this pretty nicely. In other words, that if you have a decentralized technology, it doesn't really mean that you have a decentralized economy at all. And just some perspectives on what's coming soon, hopefully. We're working now on applications to account-based systems, because of course, all I have presented exploits this UTXO protocol to measure these holding times and characterize them, but this is not available for like traditional bank accounts or credit cards or even Ethereum tokens. So we're working on a way of measuring these holding times on this kind of systems. And also there is one critical point, which is that there is a stationarity assumption at the very roots of this, but then I'm using empirical probabilities estimated on the spot for these holding times, which is not really a very nice thing to do mathematically. So we are working on having better estimators for a time varying holding time distribution and being more respectful of the stationarity assumption, basically. So this is mostly it, I would say, and a couple of references. We've recently posted most of these results in a preprint on arXiv. There is the original paper in 2003 from Wang and others, and then a couple of other papers that have influenced us in the way we developed our concepts. With this, I will conclude, and I will happily take any questions or comments.